Hi everyone, I am Rathish and I am going to present our work on how to manage high bandwidth memory automatically. This is a joint work with Kunal Agrawal, Michael Bender, Jonathan Brady, Benjamin Moseley and Cynthia Phillips. Okay, so what is high bandwidth memory? In many applications running on modern machines, keeping CPUs fed with data is a major performance bottleneck. In order to mitigate these problems, vendors have introduced a new kind of memory called high bandwidth memory into the memory hierarchy. And this memory is bonded close to the processors. So as the name suggests, high bandwidth memory has a large number of connections to the processors, allowing it to feed multiple CPUs at the same time. So where does high bandwidth memory or HBM stand in the memory hierarchy? There are three major components: latency, bandwidth, and memory capacity. Low latency is good, but high bandwidth and high memory capacity are desirable. Let's compare HBM to cache and DRAM. Cache has low latency and low memory capacity, but high bandwidth. Whereas DRAM has high latency and high memory capacity, but low bandwidth. HBM has a very different characteristics. It has the same technology as DRAM, hence HBM has similar latency as DRAM. But its capacity is limited. On the other hand, HBM has high bandwidth like cache. So HBM is neither like a cache nor like a DRAM. Then how do we use HBM? Currently, HBM is managed explicitly and a lot of effort is spent to rewrite the code for this new memory architecture. This approach is clearly not scalable. On the other hand, standard caching policies do not apply readily in HBM. Hence, we want the system to manage the HBM automatically and optimally. In this paper, we present a theoretical model for high bandwidth memory and develop algorithmic foundation for automatic management of HBM. Our model of HBM comprises a multi-core machines with P cores connecting to the HBM with P channels. The HBM has size K and the DRAM has no space limitation. As in real life, the increased bandwidth of HBM comes from multiple channels between it and the cores. There is only one channel between the HBM and DRAM. And data is transferred along any of these channels in blocks of size P. There can be up to P parallel block transfer from the HBM to the cores here. But only one block can be transferred at a time between the DRAM and HBM. The roughly comparable access costs are captured by setting the block transfer cost to 1. That is, it takes one time step to transfer a block from DRAM to HBM and from HBM to the core. In this talk, we use blocks or page interchangeably. There are two major algorithmic choices in the HBM model. First, the page replacement policy, and second, how the contention for the HBM DRAM channel is resolved, thus requiring a far channel arbitration policy. So let's see how HBM model works through an example. So in this figure, there are 4 cores, namely 1, 2, 3, 4, and each core has their own request sequence. The HBM has size K and DRAM has no space limitation. And this funnel here represents how the arbitration policy is implemented. So here we are using first come first serve policy as an arbitration policy. Okay. So at time 0, core 1 needs to get served by request A, core 2 needs to be served by page E, core 3H and core M. Basically, the arrow here represents which page needs to be served at that time step. Okay. At time 1, the channel arbitration policy decides that block A or page A needs to be transferred from DRAM to HBM. So here page A will be transferred from here to here like this in time 1. However, only one block can be transferred from DRAM to HBM, hence all other cores, namely 2, 3 and 4 will be stalled in time 1. At time step 2, core 1 requests page A, and as the page A is in the HBM, that page is transferred in time step 2 from the HBM to the core here. And the request sequence, in the request sequence, core 1 progress from here to here. At the same time, the channel arbitration policy decides to transfer the page E from DRAM to HBM here, and as only one block can be transferred from the DRAM to HBM, other cores, namely 3 and 4, are stalled. At time step 3, core 1 requests page A and core 2 requests page E. As both the pages are in the HBM, they are transferred at the time step 3 to the corresponding cores. So namely, page A is transferred to core 1 and page E is transferred to core 2 at time step 3. Hence, in the request sequence, core 1 progresses from here to here and core 2 progresses from here to here. At the same time, the DRAM HBM channel arbitration policy decides to transfer page H from the DRAM to HBM, and that page will be served later to core 3. The other core here 4 is stalled at this time step because only one core can be served using the channel between the HBM and DRAM, hence core 4 is basically stalled at time step 3. Okay, so what should be optimized in the HBM model? Is minimizing the number of page transfers? No, it is not. We show that minimizing page transfers no longer acts as a proxy of the running time as in the sequential paging problem. In particular, we show that there are request sequences such that two schedules A and B have very different characteristics. While schedule A minimizes the number of page transfers, its running time is theta p factor worse than schedule B. Hence, we directly minimize the running time. The problem statement is that given an HBM of size k and p disjoint request sequences of p cores, the objective is to find a channel arbitration policy for the HBM DRAM channel and a page replacement policy for the HBM so that the makes man is minimized. We show that the offline version of this problem is strongly at heart. We do the reduction from 3 partition. We want a competitive online algorithm to minimize the running time to serve p request sequences. So what is a natural page replacement policy? Least recently used, or LRU, is widely used and natural page replacement policy. And what is a natural channel arbitration policy? Well, first come first serve is also one of them. We show that the performance of FCFS plus LRU is far from the optimal policy. In particular, we show that there exist request sequences such that the make span of this policy is theta p factor away from the optimal one. And memory augmentation and bandwidth augmentation do not help here. We present an online algorithm called priority, and this is our main result, that priority achieves a constant competitiveness for make span minimization problem, and there is no resource augmentation is needed. This is how algorithm priority works, and the name of the algorithm comes from the fact that we assign a fixed priority to each core. Core 1 gets priority 1, core 2 gets priority 2, and so on. And in general, core PI gets priority I, and priority 1 is the highest. Okay, so in each time step T and for each core PI, we do the following. If the next page of that particular code is in the HBM, we serve that page to the core in that time step. In this example, core 1 next page to be served is A, and that page is in the HBM. And core 3's next page is H, and that page is also in HBM. However, core 2 and core P's next pages, namely E and M are not in the HBM. So hence, in the next time step, by the next time step, code 1's and code 3's next page is being served. Otherwise, that is, if the next page of code PI is not in the HBM, we do the following. We check if code PI is the highest priority code among all the waiting codes that are waiting for the HBM to DRAM channel. And if that is so, that is code PI has the highest priority, then we serve code PI's next page from DRAM to HBM. And if HBM is full, we use least recently used to evict a page. Now, there can be multiple waiting codes who are trying to get access of the DRAM HBM channel, but as the bandwidth of the DRAM HBM channel is limited, only one code get access to it to fetch a page from DRAM to HBM. Okay. So in this example, core 2 and core P's next page, namely E and M, are not in the HBM at time step T. And code 2 has the highest priority among all the waiting cores, namely 2 and P. Hence, by the next time step, code PI's next page, which is E, is served from the DRAM to HBM. Otherwise, that is, if code PI's is not the highest priority code, then code PI stalls in the time step. So in this example, code P is waiting to get access to HBM and DRAM channel. However, at time step T, there is another core, namely 2, who has higher priority than code P, and that's why code P stalls in that time step. So here is a proof sketch that why priority is constant competitive. So we divide the execution of priority into phases of length theta k, where k is the size of HBM. And we say that a core progresses well in that phase if it serves theta k requests in that phase. Now note that a core can't really progress more than theta k steps in a phase, because to serve a page from HBM, it takes unit time. It takes unit time to transfer that page from HBM to that core. So this is the ideal or best case we can hope for, that a core progresses theta k requests or theta k steps in its request sequences in a phase. Now what is the ideal or best case scenario is if all the P cores or all the active cores at that time progresses well in that particular phase. But that not necessarily always happens. And then what could be the worst case scenario? Well, only one core progresses well then. Now the priority policy implies that at least one core progresses well. That's how priority algorithm is designed. And if a core, only one core progresses well, that means that that particular core require more HBM space to progress. And in the proof, we argue that the opt also suffers for that particular core when it goes to that particular positions of the request sequence of that core. Okay, and that's why this is not really a bad case. And similar argument follows when more than one core progresses well in the interface. Okay, here is some flashback of our model and the result. So we have made a simplified assumption that the bandwidth ratio is 1:p between HBM and DRAM. The actual HBM channel ratio in today's hardware is a little bit less, but our model is asymptotically very realistic because the true cache hierarchy bundled with HBM increases the effective channel ratio. Furthermore, in near future, the HBM channel ratio is likely to increase. So we conjecture that an automatic management of HBM informed by this paper may perform significantly better. Here are some open questions that we leave for future work. First, is there a solution for the mixed-band problem when the request sequences are not disjoint? At present, our online algorithm priority works when the request sequences are disjoint. Second question, what kind of far channel arbitration policy works with other page repression policies, for instance in direct map cache? Third question, we consider the P cores to be running their own independent sequential jobs. What if the cores were running only one or more than one parallel jobs? So I conclude my talk here. Thank you.